In this video, we're going to look at the stability of phases and discuss the conditions under which phases can coexist. In other words, we're going to look at the construction of a phase diagram. Again, we're starting off here first at low temperature, and so we have solid water, in this case, in equilibrium with its gas phase along this coexistence boundary here. That's where the two would be in equilibrium with one another. In other words, what is the equilibrium vapor pressure of water above ice? That is what's given by this curve here. It's a nice smooth function of temperature. And in fact, it's a smooth function even if we keep going further past the melting point, even as we go through the boiling point. The vapor pressure is a smooth function of increasing temperature even as we go through phase transition, all the way out to the critical point out here. Now, when we expand out to a full pressure temperature phase diagram, what we see there is this, what's the sublimation curve at first, because we're going from solid to gas, turns into then the vapor pressure curve between the liquid and the gas, right? And it ends at the critical point. Talk more about that in a moment. There's also then a phase boundary between the solid and the liquid. So this is where melting occurs. Here we have standard pressure, so that would be the standard melting point. That would be the standard boiling point. There are a couple of other points you should be able to identify on this curve. One of them is the triple point. The triple point is there's one point where solid, liquid, and gas can all come into equilibrium with each other. That's the triple point, right? If the triple point occurs above standard pressure, then a system would sublime. If it occurs, as it does for water here, below standard pressure, then we'll get a normal, right? Here's standard pressure. As we increase temperature, solid melts, turns into a liquid, then it boils and turns into a gas. That's what we consider a normal phase diagram. But not all compounds do that. Caffeine, for instance, is one that goes directly from the solid phase to the gas phase and sublimes, just as CO2 does. This other point up here that you should recognize is the critical point. The critical point marks the end of the gas-liquid phase divide, right? As we go toward the critical point, delta S and delta H for vaporization both tend toward zero. How can this happen? The reason why it happens is as we're increasing the temperature at constant pressure, the molecules are getting further apart, and the density of the gas phase is increasing less rapidly than the density of the liquid phase, so they're catching up with each other. And remember, all intermolecular interactions are distance dependent. So if we get to a point where the density is equal, and indeed at the critical point, the density of the gas is equal to the density of the vapor. Therefore, on average, the distance between the particles is the same. If the distance between the particles is the same, then the interactions between all of the particles, which depend on the distance, they're also going to be the same. There is no distinction between the liquid phase and the gas phase once we get to the critical point. And that's why this phase diagram goes to a point, and we simply enter what is known as the supercritical fluid phase beyond the critical point, where you can't tell the difference between liquid and gas anymore. So hopefully now you're familiar with phase diagrams, and you can identify and interpret important features such as the triple point, the critical point, and coexistence boundaries.